So we're going to now look at a method called Newton's method. Newton's method helps us to find zeros of a polynomial. And so let's say that we have some graph in here. I don't know, let's say we look like this. And we wanted to figure out where did this graph cross the x-axis. So with Newton's method, what you're going to do is you're going to first start by looking at one value, like you're going to do a guess. So let's say that we guessed that the x-intercept was around here. Let's call this x sub 1. And so if we go up and we look at x sub 1 on the graph, and then we go and we find the equation of the tangent line. So if we were looking at the equation of the tangent line, we could, we could draw the line in here. And this would give us some value in here. So this is the equation of the tangent line at x sub 1. So what we're going to try to do is we're going to look at the x-intercept of the equation of the tangent line. And we're going to call that x sub 2. So that x-intercept, we're now going to look at our original function. And we're going to look at the tangent line at that value, x sub 2 on our original function. And we're going to do the same process. We're now going to look at this and we're going to look at the graph of the tangent line. And so notice when we look at the tangent line at x sub 2 on the graph, notice that I am getting a better accurate version of me being closer to where my intercept is on my original graph. So what we're going to do is we're going to find the x-intercept on that second tangent line, and we're going to call that x sub 3, that intercept. So we're going to just continue on this process until we get a really good estimate of our x-intercept. So now if I go on my graph and I find out what my y value is at x sub 3 on the original function, and I look at my tangent line going through that value, notice when I look at the tangent line there, I'm even getting closer to the x-intercept. And so to me, that kind of looks like it's going the same, crossing the same value that we had done before. Okay, well, then let's look at the equation of the tangent line. So the equation of the tangent line at x sub 1. So remember, to find the equation of the tangent line at a point, we needed a couple of things. We needed to know what the slope was at that point. So we figured out how to find the slope at that point. We took the derivative of our function. Let's call our function f of x. So we know our slope of the tangent line at x sub 1 is f prime of x sub 1. So we need a point and a slope. And our point would be, well, we had the x value, x sub 1, the y value is going to be f of x sub 1. So that equation of that tangent line at x sub 1, that's going to be y, right, is equal to my slope, f prime of x sub 1, times x minus x sub 1. But if we were looking at this equation of the tangent line, right, and we were trying to find when that was crossing the x-axis, that's when y equals 0. And so if I let y equal 0 there, and let's solve for x. Okay, so let's y equals 0. Let's solve for x. So plugging in 0 for y, then we have this is equal to the derivative at x sub 1 times x minus x sub 1. Did I make a mistake? I think I just made a mistake. Let's go back here. Let's see. Let's go back and look at that equation of the line. I am off on that equation of the line because I was putting it in point slope formula. Sorry about that. I was putting it in slope intercept form where I should have been putting in this in slope point slope form. So my equation of the tangent line is a little off. So if I look at this again, right, I have y minus my y value of my point, which is f of x sub 1, is equal to my slope, f prime of x sub 1, all times x minus the x value of my point, which is x sub 1. Now let's go in there and set y equal to 0. So we have 0 minus f of x sub 1 is equal to the derivative f prime of x sub 1 all times x minus x sub 1. So let's divide both sides by the derivative evaluated x sub 1. And so if we divided both sides by this f prime of x sub 1. So we would be left with, I'm going to just write the stuff that was on the right on the left-hand side now. So I have x minus x sub 1 is equal to negative f of x sub 1, all divided by the derivative evaluated at x sub 1. I'm almost there. So now let's get x by itself. We can add x sub 1 on both sides. So x is equal to x sub 1 minus f of x sub 1 all over f prime of x sub 1. But we continued to do this, right? Once we did that, we called this x sub 2. And we then did that same value. So what Newton's method says, if we have x sub n, we can find this by looking at the value right before that, x sub n minus 1, minus the function evaluated at x sub n minus 1, divided by that derivative of the function evaluated at x sub n minus 1. And this is going to estimate what that 0 of the polynomial is. Okay, so that's the reasoning behind Newton's method. This can get kind of tedious, and I might be bringing up, I'll probably bring up Desmos to help us solve this. Let's pull an example. So the example in front of us wants us to use Newton's method. It tells us what the value it wants us to start with x sub 0 equals negative 1. It wants us to find the zeros of x squared plus x minus 1 equals 0. So our function that we're using here, f of x, is going to equal x squared plus x minus 1. So x sub n is equal to x sub n minus 1 minus the derivative f of x to the n minus 1 all over f prime of x to the n minus 1. So a couple things we need to find. We need to find the derivative of this function. And that's not too bad, right? So f prime of x, that gives us 2x plus 1. And then we need to evaluate this, first of all, when x sub 0 equals negative 1. So we need to evaluate, let's plug that into our original function and see what we get back. That's what we're going to have to plug in here. So we plug in negative 1 wherever we see an x in here and simplify, we get negative 1 squared, which is 1. And then we have plus a negative 1, so minus 1, minus 1. So this is going to give us back negative 1. So far, what we have is x sub 1 is equal to f, in our case, x sub 0. X sub 0 in our case, we just told us was negative 1 minus f of x sub n minus 1, which we just found was negative 1, all over. Now we need to look at the derivative evaluated at negative 1. So if we plug in negative 1 wherever we see an x in that derivative function, that gives us 2 times negative 1 is negative 2 plus 1. Well, negative 2 plus 1 again is negative 1. So I'll divide it by negative 1. So our x sub 1 value is negative 1, 3 negatives, so that's minus 1. So x sub 1 is going to give us negative 2. So they want us to do that same thing to find x sub 2, but this time we're looking at that value of x, which we're looking at as negative 2. So a couple things we have to look at. We have to look at what is the original function evaluated at this negative 2. So plugging in negative 2 wherever we see an x, we get negative 2 quantity squared plus negative 2 minus 1. Well, negative 2 squared, that's 4, minus 2 minus 1. That's going to give us back 1. And plugging that into our derivative function. So plugging in negative 2 wherever I see an x in my derivative, I have 2 times negative 2 plus 1. So negative 4 plus 1, that gives us back negative 3. So our x sub 2 value, this is going to be our x sub 1 value minus f of x sub 1 all over f prime of x sub 1. So this equals negative 2 minus, so f of x sub 1, that was our positive 1, all over f prime of x sub 1, which was negative 3. So this gives us negative 2 plus 1/3. So negative 6/3 plus 1/3 is negative 5/3. Or negative 1 and 2/3. Okay, so they wanted us to look at that, but they also, that was part A. Part B was start when x sub 0 equals 1 instead of x sub 0 equals negative 1, and then find x sub 2. So again, we have our equation x squared plus x minus 1 equals 0. We're trying to find out where does this cross the x-axis. They gave us the x value to just guess and check. And they said, now let's use x sub 0 equals positive 1. Our f of x value, again, is the same function, x squared plus x minus 1. Derivative still remains the same. So f prime of x, that is 2x plus 1. Did I do that? And so now to find x sub 1, this is going to equal x sub 0 minus f of x sub 0, all divided by f prime of x sub 0. So let's go in and plug in 1 wherever we see an x. We get 1 squared is 1, plus 1 is 2, 2 minus 1 is 1. So f of 1 simplifying, we get 1. Plugging in positive 1 into the derivative, we get 2 times 1 is 2, 2 plus 1 is 3. So f prime of 1 gives us back 3. So we get our first value, x of 0 is 1, minus f of x of 0, which we found was also 1, all over f prime of x of 0, which we found to be 3. So in this case, we have 3/3 minus 1/3, which is 2/3. So we want to apply the same process now, but this time we're using x sub 1 is 2/3. And so we want to go in and we want to plug that into our original function. So let's go in and put a parentheses wherever we see an x in the original function. So we have parentheses squared plus a parentheses minus 1. I said that was 2/3, but I wrote 1/3. This is 2/3. Okay, so order of operations, exponents first. So 2/3 quantity squared is 4/9. Plus, so I notice I'm going to need a common denominator here. Let's just do that now. So let's multiply that 2/3 by 3/3. So that is a 6/9 minus 1 could be rewritten as 9/9. So we got 4 plus 6 is 10, 10 minus 9 is 1. So this would equal 1/9. X sub 2 equals 2/3 minus f of x sub 1, which we just found to be 1/9, all divided by, now we have to look at the derivative evaluated at 2/3. So go in and plug in 2/3 into this derivative function, we get 2 all times x, which is 2/3 minus 1. So we got 4/3 minus 1. 1 is the same thing as 3/3, which gives us back 1/3. So over here we have 1/9 divided by 1/3. So I'm going to rewrite that as a division problem, that division right here as a multiplication. So this is the same thing as 1/9 times the reciprocal of the denominator. So times 3. Or 3/1 if you want. Order of operations says multiplication comes before addition or subtraction. I notice I can reduce here. 3 goes into itself once, 3 goes into 9 3 times. So this leaves us with 2/3 minus 1/3 which is 1/3. Okay, so just doing 2 iterations, we found, or we're guessing, that our x-intercepts right now are between -1 and 2/3 and 1/3. Let's look at the graph of that. Okay, so I brought down the derivative wrong. Remember, the derivative had a +1 in here. +1. And I had written it when I was carrying it down as a -1. So this should have been +1. That's going to change things a little bit. So I would have added 3/3 to my 4/3, which gives me 7/3, which changed things over here. This should have been a 7/3 in the denominator. So rewriting that complex fraction as a multiplication problem, that's 1/9 times 3/7. And so again, we can simplify. 3 goes into itself once, 3 goes into 9 3 times. So right here, this gives me 2/3 minus 1/21. I'm going to need a common denominator. So let's multiply 2/3 by 7/7. That's 14/21 minus 1/21. That's going to give us 13/21. Okay, so let's look at the graph of this and see how close we got for our x-intercepts. Okay, so graphing this function, x² plus x minus 1, notice there's 2 intercepts. Our first one over here, we have -1.6. And our other one over here at x equals, where we had chosen x equals 1, we have 0.618. Okay, so let's go back and let's put our answers in decimal form just to see how close we are. So we have that 13/21, and we have the other one, which was -1 2/3. Well, no, -1 2/3, that is -1.6, and that 6 is repeating itself. So that -1.6, I think it was 83 or something like that. That's pretty close. And then 13/21. I'll pull my calculator out. So plugging 13 divided by 21 in the calculator, you get approximately 0.619. So again, if we look at that, here was 0.618, so we're really close. And here was -1.618, and I had -1.6 with a bar over it. So we got pretty close by just doing that 2 times. The thing is you guessing for the correct value to kind of estimate where you are. Kind of want to go back for a second to look at that original example I was showing you on and explaining Newton's method. Notice that, I said, okay, we have to just kind of guess and then look at the tangent line and find out where that tangent line is equal to 0. And that's our other x value that we're going to use to guess and apply this method. But if I had chosen something, what if I, first of all, had chosen my x value to be here, and I looked at the equation of the tangent line, that's going to be a horizontal line. So that's never going to cross the x-axis. So that's not a good guess. And it's possible maybe I had guessed something on the other side, What if I had guessed something here, but this function had ended up maybe turning around? So maybe this function in here had turned around like this and went up forever. So if I had chosen a point over here on the left-hand side of that maximum, I would never then get that x-intercept. So part of this method is guessing correctly. Okay, let's look at another example. So this next example says, use Newton's method to find an approximate solution to x times e to the x equals 1. And we want to start with x sub 0 equals to 0 and go out and find x sub 2. So we first need to define our original function because it's as an equation and it's not saying find where your intercepts are. So we can say this is the same thing. Let's solve this so we're equal to 0. And so if I subtract 1 on both sides, I want to know what are the x-intercepts of x times e to the x minus 1. We're going to need to find the derivative of this function, so we might as well do that now. If I look at this, I notice that taking the derivative, we're going to need to use the product rule. So if we look at the derivative of the first function, and let's consider that first function as x. So the derivative of x is just 1 times the second function, e to the x, plus the first x times the derivative of the second function, e to the x. Well, the derivative of e to the x is just e to the x minus the derivative of 1, which is 0. So our derivative of f of x, we can rewrite if we wanted to as e to the x plus x times e to the x. So we want to know, looking at f of 0. So plugging in 0 wherever we see an x in our function. So we get 0 times e to the 0 minus 1. So this just gives me back negative 1. Now let's plug in 0 into the derivative function. So if we plug that into our derivative function, we get back e to the 0 plus 0 times e to the 0. So that's just going to give us back positive 1. E to the 0 is 1, 0 times anything is 0. And so x sub 1, next value we're going to look at is the same thing as x sub 0 again minus f of x sub 0 all over the derivative f prime of x sub 0. So our x sub 1 value is 0 minus f of x sub 0 was negative 1. So minus a negative 1 divided by f prime of 0, which was 1. So our x sub 1 value is now equal to 1. So we now need to go in and apply this and find x sub 2. So we need to look at what is the original function evaluated at 1. So we have 1 times e to the 1 minus 1. For now, I'm going to just leave it as e to the 1 or e minus 1 is fine. And plugging 1 into our derivative function, we have e to the first power plus 1 times e to the first power. So this is going to give me e plus e, or 2e. So I know my x sub 2 value is equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1. Looks like my pen is starting not to work anymore. So x sub 2 is equal to x sub 1, which we found to be 1, minus f of x sub 1, which we found to be e minus 1, all divided by f prime of x sub 1, which is 2e. So this is where I would probably plug it into the calculator and get an estimate. So be careful when you plugging in that numerator, put parentheses around it. So I have 1 minus parentheses e minus 1. And my parentheses divided by 2e. I would put parentheses around 2e. And we get that that is approximately 0.68. Okay, so again, let's look at the graph of f of x and look at how close we had gotten. So looking at our graph of our function, let's look at where the intercept is, and it looks like it is at 0.567, and we got 0.6. Okay, so pretty close. If we continued on with this process, we should get even a closer answer. And so it might ask you to continue on with this process until your decimal places continue to repeat itself a certain number of digits out. So our next example says, use Newton's method to approximate the solution of 3 minus x equals natural log of x. Start with x of 0 equals 2 and find x of 2. So again, we want to, if it's given us an equation, we want to set it equal to 0 and define that to be our function. So if we subtract natural log of x on both sides, we can say, well, this function f of x, let that be 3 minus x minus the natural log of x. We're trying to find out what are the solutions? When is this set equal to 0? We're going to need to look at the derivative of our function. So the derivative of 3 is 0, minus the derivative of x, which is -1, minus derivative of natural log of x is just 1 over x. So we're going to need to look at what is f of 2, plugging in 2 wherever we see an x in our original function. We have 3 minus 2 minus the natural log of 2. So 3 minus 2, that's 1, minus the natural log of 2. And now let's look at the derivative evaluated at 2. So if we look at that, that's -1 minus 1 over 2. So -2/2 minus 1/2, that's -3/2. So far what we have is x of 1 is equal to x of 0, which is 2, minus f of 2, which we found to be 1 minus natural log of 2, divided by f prime of 2, which we found to be -3/2. So x sub 1 is equal to 2. I notice here I have a minus and a minus, so really plus 1 minus natural log of 2 all over 3/2. Invert multiply. So x of 1 is equal to 2 plus 2/3 all times 1 minus natural log of 2. So this is where we might want to put it into the calculator now, especially if they had asked us to go on and figure out, don't stop until you keep on getting the same decimal. So 2 plus 2 divided by 3. And then this is all times 1 minus natural log of 2. So if I did this correctly, I get x sub 1 is approximately 2.2046. Okay, so now we can find our x sub 2 value. X sub 2 is equal to x sub 1, 2.2046 minus f of x sub 2. So if we look at this f of and plug in 2.2046, wherever we see an x in the original function. So we have 3 minus this 2.2046 minus natural log of this 2.2046. So plug it in the calculator. And this is where I might keep it as an exact answer and just plug it in 3 minus the answer I had before, minus the natural log of the answer I had gotten before, just to be a little more accurate. But I can do that in this calculator. So 3 minus this, my answer before, minus the natural log of my answer before. So if I do that, this is approximately 0.0048, actually 49, because of rounding for a while. So here we have this 0.0049 divided by, now plugging in this 2.2046 into the derivative function, which is this one. So that's going to give us -1 minus 1 over this 2.2046. Which gives you approximately -1.4536. Okay, we're almost there. X sub 2. We're going to put that over that -1.4536 here. Minus and a minus is plus. So I have that 2.2046 plus 0.0049 divided by 1.4536, which gives us approximately 2.208. So notice that we're pretty close to what our x sub 1 value is, 2.20. So we're up to 2 digits after our decimal being the same. This is a 4 and this is an 8. So you can see that we're pretty close. And if I continue to do this, we're going to get closer and closer. Okay, so there is Newton's method for you. So tomorrow we're going to look at the last section of this chapter, which is on antiderivatives. And we've already actually looked at antiderivatives a little bit. So kind of going backwards, thinking of what can I take the derivative of to get this, or yeah. If I was given a function working backwards, what was the function I had to take the derivative of to get this function? Okay, so let's stop there for today.